going to continue our presentation, but first I'm sorry because I forgot to introduce myself. My name is Fauzia and I will be the moderator for today's presentation. And we have heard presentation from the group 4. And now we're going to hearing the presentation. The next presentation is from group 10. This is Intan and Ilham and Kevin. So I will give it to them. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. So before we begin our presentation, we have some video game. Still related about car, but it's kind of more interesting because it's a scene from a movie. So please enjoy. So we can see from here, the suspension is lowering as the man will push the button. Maybe we can repeat the video. Maybe the video is dead. So we continue to the presentation. First, let me introduce our group. We're from group 10. I'm Ilham Nur Pratama, and she's Juniar Intan Rahmania. You can call her Jun. And this is my friend Kevin Rio Harristyando. You can call him Kevin. So, what we're gonna discuss this morning, this beautiful morning, is how to go back. Yeah, so what we're going to discuss is still related to car, related to increasing the car performance. It's the modeling and simulating of car suspension using numerical method. If the first group that have already presented before, they consider car performance will be priced if we concerned about the aerodynamics and the drag force. But that's not the only thing that matters in car design. If we're going to talk about car racing, especially in circuit racing, we're not just need an aerodynamics, but we have to have a proper suspension to make our cars not more kebanting, buang swing, not more swing when we're turning in high speed. Next. Yeah, this is the introduction. Now, there's three types of suspension. There's an active suspension, semi-active suspension, and passive suspension. I'll begin to tell you about the passive suspension. Passive suspension is the usual suspension that most of major of people use the passive suspension. What's the meaning of passive suspension? Passive suspension is the original from the manufacturer. So it only has shock breaker and the spring. It's the passive suspension. And then there's semi-active suspension. This is usually found when you're try to lowering your car to get more aesthetic view, chapter view. Yeah, this the famous product of semi-active suspension is coilover. If you ever know, what's the difference between the passive and semi-active? When passive suspension, you only have one configuration of suspension, but if you use semi-active suspension, you can adjust your suspension to spring and shock breaker that you want. For example, if you want to drive in bumpy road, you can set your suspension to be more elastic. And if you want to drive in circuit, you can set the suspension to be more stiff and low. So you can have low swing, low simpangan. But there's disadvantages of using semi-active suspension. The disadvantage is you just can only set the suspension when the car is stopped. I mean, you have to open your hood and you have to putar-putar knob yang ada di atas in the upper of the suspension. Yeah, that's the disadvantages. So there are the active suspension. The active suspension is the one that I've already shown before in the videos. When the driver wants to lower his car, he just press a button and the suspension is drop, langsung turun, langsung drop. So we don't have to go under the hood and putar-putar knob atasnya. Yeah, so that's the types of suspension system. And next. Yeah, so for the method on MATLAB, we're using second method for finding proper pressure for the spring to have performance on circuit, I mean on straight line. Next, yeah, this is the mathematical model. We have the a body of a car, symbol SMS, and the spring it's KS, and the damper is BS. The spring is the spring itself, and the BS it's the shock breaker, and the MUS is the mass of the wheels and rims, wheels and tires. Next. So this is the equation that we use for the MATLAB. Maybe Kevin can explain.
Okay, I will continue this presentation. First, I will talk about the simulation of the paper of our paper. In the simulation, we use MATLAB when there is in theory we find from the other paper we found like there is a graphic like when the suspension of the car is like bumping into a hole or like some disturbance, you will get like the suspension will be like a bumpy. First, it will like a bumpy first, like 1 second or 0.1 or what, and then they will like stay. And this is the simulation like when the suspension will get some disturbance from the road, and they will stay. Now I will tell the system control from this simulation of like Ilham said. We will make some system control of the suspension system. First, the road disturbance will push the suspension system, and when the suspension system gets force, then hydraulic actuator will give some force for the suspension system. When they get the force from hydraulic actuator, they will get information, and then we'll send to main loop controller, and we can set the main loop controller to be automatic, like from the video. We just push the button, and then the information from the main loop controller will make the suspension system of the car will get low or get high. And then this is the equation from the this is the equation from force loop system control in the main loop controller. First, YT equal Hp with which means Hp is proportional gain, Et is equate function that is changing with using time, and then Hd is differential gain, and A is integral gain, which is Hd, Hp, A has been on the data of the car. From the TP is 1000, TD is 4000, and TA is 5000. And the control response of TP using the rise time is like rise time. First, I will tell rise time, overshoot, settling time, and steady state error. Rise time is like when you like give some force and then you will respond of the force. That's what rise time means. Like you need time for response you need time to respond the force at rise time. Overshoot is like percent of steady state error per rise time. Settling time is like when you need to respond, it will change the system control of the modeling. And steady state error is like when the force from out like not flat bumpy road or some kind of road that disturbs it will give the TP, TA, TD probably different each other. First TP and from the TP in the race time, TP will be decreased and the overshoot will be increased and the settling time probably small change and then steady state error will be decreased. Why? Because proportional gain from the system control will be something like that, and TA will be decreased and then increased, and then settling time will be increased, and steady state error will be eliminated because the from the PA integral gain there will be no steady state error because steady state error will be like 0, and the differential gain in the race time will be small change. Like it will be changed depend on the time or some situation, and the overshoot will be decreased, and settling time will be decreased, and steady state error will be probably same.
For this presentation, I will show you how my MATLAB works. It's for method of modeling and simulating car spring. So here we have the equation. We have 100 represent the mass of the car, mass of the total wheel approximate to 25 kilogram. And we have the equation here. And we also have the constant of tire that equals to 17,000, and we have C, which is elasticity number of bumpy roads. It's close to 1 for bumpy roads and near to 0 when it's on smooth road. So we're going to simulate how much the deviation of a spring would run if we want to have a proper damp of a spring. So let's run. We're gonna run, and what we have here is here, and the first one is the first guess. I'm sorry, I forgot to tell. The first guess is 0.15 centimeter meter, and 0.2 meter. It's equal to 15, 60 centimeters, and 20 centimeters. And from the iteration we get from the second method, which is the 0.15 and 0.2, and this is the first iteration, and next second iteration we have a proper spring damper is equal to 0.054, but it has 270 error, so we're gonna take another iteration. So we have the closest one, and we have the iteration number 2. We have 0.5313, and we have only 1.6% of error. So we're going to the next iteration. It's the final iteration. It's only have 0.016 errors. It's very small, and it equals to 0.05 meters. It's equal to 5 centimeters. So the proper spring on a smooth road is only require 5 centimeter of press. So we don't need a lot of press when we're going to make a good spring. So that's all from me. Thanks for the presentation.